So I'd like to just talk about all of it. Is that all right? If I go through it quickly? I don't know why this is. Especially the second blue question. Number one, it says, does the amount of solution added to the water affect the volume ratio? Well, water is H2O always. It doesn't change with any of the solution we use, so this is no. It doesn't change the ratio. It asks you in the reading to find the volume ratio. Okay, the paragraph right before this one right here, it tells you to find the volume ratio. So here's how you do it. It's real simple. Volume ratio is equal to volume of H divided by volume of O. And so let me give you some sample numbers. This is what somebody had first hour. Volume of H was 6, volume of O was 3. And so the volume ratio is 2. That's what you should have found. The volume ratio should have been 2. Now there's lots of reasons why it might not be. For instance, the oxygen has a tendency to break down the electrodes, and not all go in the gas. Some of you saw some like brown stuff in the oxygen test tube. That's why. Okay. So let's find the mass ratio. To find the mass ratio, we've got to find the mass of each of these, and I'm just going to use these numbers right here. So it's this. Mass ratio is equal to mass of H divided by mass of O. So the mass of H, if we've got 6 cubic centimeters, we can say M is equal to V times D, and this is for H. Or M is equal to 6 times 0.000084, which is, I think it's 0.0005 grams. I better check. Yeah, 0.0005 is the mass of H. For O, same equation. M is equal to V times D, or M is equal to 3 times the density of O, which is 0.0013. And you get M is equal to 0.0039 grams. I better check that too. Yeah. And then to find the ratio, we just say mass ratio is equal to 0.0005 divided by 0.0039, which is equal to 0.13. That's what you should have found. What this means is, for every 1 gram of oxygen, the bottom number, we have 0.13 grams of the top number, hydrogen. So hydrogen, even though there's twice as many hydrogen atoms, hydrogen has a very, very small density and doesn't make up a lot of the mass of water. Does that make sense? Okay, so this is what the mass ratio is always for water. It's always 0.13. And we actually did this last semester when we did the law of definite composition lab, which you probably don't remember, but we did it. Number 1, it says, suppose that during experiment 6.2, some oxygen gas was inadvertently bubbled outside the test tube. How would this affect the calculated volume ratio? So here's how we found it. Volume ratio is equal to V of H over V of O. If some of the O was inadvertently bubbled out, it's going to make the O less, and it's going to make the volume ratio do what? Increase. So this would give you a volume ratio greater than 2. Number 2, suppose that when conducting 6.2, a student allows the hydrogen gas to completely fill the test tube to the point of overflow. How does the air affect the calculated volume ratio? Well, same equation. Volume ratio is equal to V of H over V of O. If the hydrogen is overflowing, that number is just going to, if the test tube holds 50 cubic centimeters, it's going to stop at 50, right? But what's the oxygen going to do while that's happening? It's going to keep filling. And so the oxygen is going to actually be higher than it should be, and that's going to make the volume ratio less than 2. On number 3, does the volume of hydrogen plus the volume of oxygen collected equal the volume of water broken down? No. Okay, and this is why. Volume is not conserved. There's no law of conservation of volume. So if you ended up with, right here, 6 plus 3, 9 cubic centimeters of gas, that doesn't mean that you broke down 9 cubic centimeters of water. As a matter of fact, when a liquid turns into a gas, it takes up 1,000 times more space. So the same thing kind of happens here. You're taking up 1,000 times more space with the gas than you are the liquid. So really, you broke down a very small part of the liquid. As a matter of fact, we can add it together. 0.0039 plus 0.0005. What's that? 0.0044. You broke down 0.0044 grams of water. What's the density of water? Anybody remember?
1.
It's 1. So the volume of water you broke down was 0.0044 cubic centimeters of water. So 0.0044 cubic centimeters of water turned into 9 cubic centimeters of gas using these numbers here. Okay? Let me move this up so we can see 4, 5, and 6. Number 4. I'm going to have to erase this too. What's the combined mass of oxygen and hydrogen that would be produced by the decomposition of 180 grams of water by electrolysis? Mass is conserved, so it's 180 grams. Okay, mass can't be created or destroyed, so if you start with 180 grams, you have to end with 180 grams. And then if all the hydrogen in part A were burned in air, when you burn it, you're adding oxygen to it. And so you're turning that back into water, right? So what mass of water would result? Will we get the 180 grams back? Number 5, in decomposing water, suppose you'd filled many test tubes with gas. As the water disappeared from the beaker, suppose you refilled it without adding more sodium carbonate. You would have found that the ratio of hydrogen to oxygen produced remains constant. What does this tell you about the source of the gas? I'm going to write this in 2 parts. The source of the gas had to be the H2O. And then what does it tell you about the sodium carbonate? I'm just going to say not used up. The entire purpose of the sodium carbonate, the stuff that made your fingers slick, you know what I'm talking about, was just to make it go faster. You could run electricity through water and still produce hydrogen, oxygen, gas. It just happens very, very slowly. There'd never be an amount that you could measure. So the sodium carbonate made it go faster. And then the last one, what would be the ratio of the volumes of gas in the 2 test tubes if you'd interchange the connection of the terminals of the battery halfway through the experiment? Well, let's look at this. If we have, we'll say these are test tubes. I'm not an artist, so bear with me, okay? Halfway through the experiment, let's say that this test tube is half full of hydrogen. How much oxygen should you have in the other test tube? How much? A quarter. Half of half, right? So a quarter of a test tube. If we interchange the terminals, then now you're going to collect oxygen in this one. So we're going to get another quarter tube in that one, and you're going to get a half tube of hydrogen here. So it looks like we have the exact same amount of gas. What's that ratio going to be?
1 to 1.
It's going to be a ratio of 1. So the answer to that is 1, and this is the reason why. Any questions about that? Okay, so let's talk about the lab we're going to do today. So turn to 6.4. We're going to finish this. This 6.4 lab needs to be turned in before class tomorrow. And you also need to turn in the nature of chemical reactions that we started yesterday, which some of you have already done. Okay? Here's where we're going to pick up. Right in this paragraph here. It says the reaction at first is quite vigorous. However, to make sure that it's complete, allow the mixture of zinc and acid to stand overnight. That's what we did. In the next period, pour the liquid from the test tube into an evaporating dish that you've already masked. And so, every table has an evaporating dish that looks like this. Make sure that it's dry, and you need to mass it and write it down. Make sure you mass it accurately to the hundredths place. Last hour, it should be like 20-something. I don't know how many times I walked around and I saw people have the mass is like 3 grams. Okay, that's nowhere close. I have no idea how they would get 3 grams. Okay, obviously, maybe I need to give a lab practical on how to mass things. Okay, but pre-mass that. We want to know what it is because you'll need it at the end. Then you need to pour the liquid that's left in your test tube into the evaporating dish. There might be some zinc left. There might not. Doesn't matter. Take 5 cubic centimeters of water, pour that in your test tube, and then pour that in the evaporating dish too, so we can wash out anything that's left in the test tube. Okay? But don't let any zinc, if you have leftover zinc, don't let it go into the evaporating dish. You're going to take the leftover zinc, which is going to be the mass of zinc remaining. You're going to take the leftover zinc out of the test tube. You're going to dry it off, put it on the balance, and see how much you have, okay, what the mass of it is, and put it right here on the mass of zinc remaining. To find the mass of zinc reacted, take the mass of zinc used minus the mass of zinc remaining. That's going to give you the mass of zinc reacted. And then you're going to take all the liquid that you have in your evaporating dish and evaporate it off. Okay, so once you get your basically 10 centimeters in there, 10 cubic centimeters, start heating it. You're going to get a white crystalline solid. It's zinc chloride is what it is. It has a very low melting point, so if you watch it, it'll turn into it'll all of a sudden appear as a kind of a white puffy solid. And then if you'll watch the edge around where it's touching the evaporating dish will start to melt. Once it starts to melt, all the water's gone, and you can turn everything off. And if we want to know what the mass of that is, that's the product. Okay, this is the white stuff that's left in there. I put up here how to find the ratio. You're going to take the mass of zinc reacted, divided by the mass of the product. You should get a decimal. In other words, this number is going to be bigger than this number. So go ahead and get in your groups and get busy.